So I want to solve the differential equation y prime prime, so the second derivative of y, minus 2y prime, so the first derivative of y, plus 2y is equal to 2 times e to the t. And I want to solve it using the Laplace transformation. So I have as initial conditions y of 0 is equal to 0 and y prime of 0 is equal to 1. So I take the Laplace transform of both sides and I get so the Laplace transform of the second derivative of y is s squared times capital Y, so capital Y is the Laplace transform of y, minus s times y times y of 0, minus y prime of 0. And the Laplace transform of minus 2y prime is minus 2 times, in parentheses, s times capital Y minus y of 0. And the Laplace transform of 2y is simply 2 times capital Y, by capital Y of s each time. Yes, and the Laplace transform of 2 times e to the t is 2 over s minus 1. So now I can solve for capital Y. So I can first use my initial conditions, and then solve for capital Y. So I factorize and then throw everything else on the other side. So on the I get that capital Y is equal to 2 over s minus 1 times s squared minus 2s plus 2 plus 1 over s squared plus minus 2s plus 2. Okay. And so now this 2 over s minus 1 times s squared minus 2s plus 2, I can use partial fraction decomposition. So I can write it in form like a over s minus 1 plus bs plus c over s squared minus 2s plus 2. And so if I do partial fraction decomposition, I get that a is equal to 2 and that bs plus c is equal to minus 2s plus 2. And now this s squared minus 2s plus 2, I can write it as s minus 1 squared plus 1, okay? I can also factorize it using complex numbers if I want, but it's a lot more complicated then to deal with, because if I simply write it like that, I can then use the shifting theorem for the Laplace transform, okay? Remember that, like, if you have s minus something, instead of simply s, you just shift everything with the something. Okay, so if you have s minus 1, instead of simply s, okay, simply have s minus, if you have s minus 1, you shift it with e to the nt, if I'm correct. Okay, that's what we will do here. Like if you have, here we will have s minus 1, so we will shift it with e to the t. Okay, so yes, so we can rewrite everything as minus 2. Wait. Yeah, this minus 2s plus 2 over this thing here, we can rewrite it as minus 2 times s minus 1. Okay, we can factor out the minus 2 here. Over this s minus 1 squared plus 1 plus this 2 over s minus 1 plus wait, what? Where does that come from? Yes. Yes, it's this part here. Okay, we did the partial fraction decomposition of this part here. That's what we got, those two things here. Now we need to remember that we had this part here. So again, this part here for the denominator, I can write s squared minus 2s plus 2 as s minus 1 squared plus 1. And so now, again, here we have s minus 1, so I can use the shifting theorem. I get e to the t, and then like we know that the Laplace transform, the inverse Laplace transform of s over s squared plus 1 squared, so 1 is simply cosine of t. And here we have plus 2 times e to the t, we have the 2 here, and we know that the inverse Laplace transform of s minus 1 is e to the t. Then we have also here, we will have s minus 1, so we will just shift everything with e to the t, and then we know that the inverse Laplace transform of 1 over s squared plus 1 squared, okay, so 1, is sine of t. And so our resulting function y of t is equal to minus 2e to the t cosine of t plus 2e to the t. This is a 2 here. plus e to the t times sine of t. And that is our final result. Yes.